Uncertainty is one of the main challenges in robotics, pretty much exemplified in localization, where errors are building up. So here you see a robot driving on a circle and mapping the environment, and what happens is the map is distorted as it drives because error is building up. In this lecture we're going to study how we can formally describe this. So one way to think about this is to think about a Gaussian distribution that represents the position of the robot. So let's say the robot is right here, we know that pretty certainly, so we have a very narrow Gaussian, which I draw like that, and the Y position of the robot is around there, so we have a pretty narrow Gaussian that represents that here. Now what happens, the robot drives on, and somehow that Gaussian distribution becomes a little wider, and so it continues driving, and so the Gaussian just has a new mean, which is here, becomes wider again and wider again, and finally becomes really huge at the end, which might look like this. And of course the same happens on the y-axis, so we have some kind of Gaussian distribution, looks like this, then it gets wider, looks like maybe like that, and so on. So you might get the idea. We could now think about also representing that as a two-dimensional Gaussian. So if you look at it on a 2D plane, and I just draw that into the same figure here, you might have something that has a Gaussian shape like this, and then for the y-axis like that. So these circles that I've drawn here are representative of the variance in the x direction and the y direction. So you have a circle like this, and this is what I plotted while the robot was moving. Now the question is, how do you calculate that new variance as the robot drives forward? So what happened in the previous picture is that we have a random variable x, the position of the robot, which was given by a Gaussian distribution, which has some kind of standard deviation of sigma x. And then the robot is moving some kind of function f of x, and it has a different standard deviation. Let's call it sigma x prime, not to confuse it with y, which is actually the random variable capturing its y component. So what we're interested in is some kind of relationship that gives us the new standard deviation of x prime given this function f of x and the old standard deviation s of x. Now let's assume we know that function f of x. What we can do is we can think about how a very small change in x will actually affect the outcome x prime. And with that we already have the error propagation law. We look at the derivative of f of x and multiply it with the standard deviation of the input. Now if we are interested in the variance, which is the square of the standard deviation, we write down dx prime dx square times the variance of x. And now more generally, if we have any function y equals f of x, the variance of y is given by the derivative of y with respect to x squared times the variance of x. So this is the error propagation law in one dimension. So what happens when we have multiple dimensions? So on the odometry example, we already have 3 dimensions for the robot position, and we have 2 dimensions for the robot inputs, which are the wheel speed of the left and the right wheel. Let's think about the general case of having m outputs and n inputs. And one thing you need to know is best is to write this down in matrix notation, where we use matrices which keep the variances on their diagonal entries. So for our outputs, let's call them all y. We go from y1 to ym. And for now, everything else is 0 in this matrix. This is our output covariance matrix. And we will have an input covariance matrix, which I place here, where I have n inputs. And of course, everything else is 0 for now. Actually, it doesn't have to be. You might very well have variables that are related to each other, and somehow changing one will also affect the other. And so in that case, these entries are not going to be 0, but actually contain the covariance entries of those variables. And so that's also why all of these matrices are called covariance matrices. And this is also a covariance matrix here. Okay, let's look at these matrices. And we are talking about the variances here, so everything is squared, it's not the standard deviation. And this is an m by m matrix, because I have m elements on the diagonal. And this is an n by n matrix, because I have n elements on the diagonal. Now we already know if you want to convert these two dimensions, we need other matrices here, one to the left and one to the right, which are gonna be m by n and n by m matrices. Now if you calculate that or multiply those through, you will get a m by m matrix. And so we've been talking about the derivatives. We need to calculate the derivatives with respect to one to the other, and we will need to fill these matrices with those. And so let's think about that real quick. We will calculate the derivative of the input. So the inputs are y, the output with respect to the inputs, which are x. Now this is going to be going down to m entries, so we will enumerate it from delta from y1 to ym, while this row is going to be enumerated till x n. So this row stays, the y stays 1. In the last row we are going to look at the yms, and then this goes down to xn, and this goes down to x1, x1. So here we have all the x1s, and here we have all the xn's, and then similarly for the columns. So only one thing changes per column and one thing changes per row. Now this matrix is going to be the transpose of the first matrix. So we start with the same entry, and then we take this one and place it there, y1 dxn, and yes, we have a matrix with n rows, and so we want to end up with m columns. So we go till ym here, and now this time we keep x1, and here at the very end we go to ym and xn. And one thing you need to know, I used a different symbol here, which is the delta symbol that tells us that we are looking at a partial derivative of dy to xj. So now if you work these out, you will find that you get exactly the same result. Each of these variances is going to be the square of the partial derivatives times the input variance. And depending on whether you have these entries to be 0 or not, and depending on what the partial derivatives actually calculate to, the covariance matrix entries are not necessarily be 0, but you can always look at the diagonal of it, which gives you all the quantities you are interested in. Now let's get back to the... So for odometry we have equations that relate the previous position of the robot, x, y, and theta, to its new position by giving the wheel speeds of the right wheel and the left wheel respectively. So the equation is going to look somehow like this. You have a vector with the previous position, and then you add the changes in x, the changes in y, and the changes in delta theta to it. And those I wrote down here to the right. And the key idea is that you take the displacement of the right wheel, the displacement of the left wheel, and you calculate the turning angle from that and the displacement that the robot moves. So what we want to expect here is that we have some kind of matrix that contains all the variances for our position. That is sigma x, sigma y, and sigma theta square, and is otherwise 0. Or actually it doesn't matter. Let's not confuse ourselves with that. But these are the things we care for now. And we have a covariance matrix for the inputs, which is the variance of the left wheel, of the right wheel, and the variance of the left wheel. And those we know are not related to each other, so we place zeros here. And now we have to take all the partial derivatives of the function f with respect to the changes in the right wheel and the changes in the left wheel. So this is a 3×3 matrix. Just do a sanity check here real quick. This is a 2×2 matrix, so we expect a 3×2 here, and we expect a 2×3 there. Now we have two inputs, so this is going to be the column for the right wheel, and this is going to be the column for the left wheel, and then we have the three outputs. So let's write down SR divided by nabla delta x, nabla delta SR delta y, and delta theta finally. And we do the same thing for the left wheel, left x, y, and theta. Okay. So this matrix here is going to be the transpose of that one. So it's a 2×3. We start with the entry here in the top left, SR and delta x, and then we work our way down, SL delta x, and then we go along the first column S Y S R delta theta, and now the second column delta SL SL, and finally d theta. So are we done now? Let's see what we have actually done. We have created a relationship that relates the variance of the inputs, which is the wheel slip, to the variance of the position of the robot. So every time the robot moves, all of these variances are going to increase a little bit. And this should be pretty much linear, so it should be something like a variance that is first like this and then goes like that and grows and grows. And the question is, how does it change when you look at the y dimension or if you look at the x dimension? Is that giving us the effect that we've seen on the first slide at the beginning of this lecture, that the arrow grows much further in the y direction than it does in the x direction? Or have we forgotten something? Well, if you think about it, we haven't actually done anything here to preserve our old variance. So what we need to do at least is we have to make a big plus here and add the covariance matrix that we previously had in order to do something similar than in the odometry update law. So we also have our covariance matrix that keeps track of the variance in x, y, and theta. So if we don't have that, I think it's very clear that this variance will always be the same. This variance is never going to change. This variance can actually never build up anywhere because it's just going to be given by these elements. So we have to use the previous variance. Now, so this is not the same variance as that, so let's call this Cx prime, and this is the original Cx. So this is Cx prime, let's put the prime here not to create confusion, and this is the current Cx. Now we actually have to do the same thing. We have to again do all the partial derivatives on this function here with respect to x, y, and theta this time. So again, we have input variables, which are the x, the y, and the theta column. And now we take the derivative with respect to the input variables, which are the previous positions. So that's with respect to dy, and finally to d theta. dy, dx, dy, dy, and I can already tell you these are going to be 1s, and dy, d theta with dx, d theta with dy, and d theta with d theta. And same here, just the transpose, and maybe I don't write this out completely. So we have the row going down here this time, and then we have some middle column that I will spare myself of doing, and we have dx, d theta here, and at the end we have d theta, d theta. Okay, so now we have the full expression. This is something where we add variance from the wheel slip every time we move, and we take the old variance and look at what happens to it when the robot moves. And this is actually very important, because if you think about what happens to the robot, is just the motion alone will change the variance. Why is that? Well, if you consider the robot driving this direction with a very tiny error in theta. So this is a small error in theta, and it has a current variance like this. So we have some uncertainty in the x direction, we have some uncertainty in the y direction. Now if the robot moves and the error here is just very small, it might end up at a completely different location. So that's why, and so actually you could even draw the distribution over the theta angle here, and the bigger this is, the bigger is going to be the propagation of the error in the y dimension. And this is actually explaining what we've seen in the beginning, that when the robot drives forward, the error in the y direction keeps increasing and increasing. So now what we can do is we can calculate all these partial derivatives, fill them in, and then simulate this in Matlab. So I niceified this a little. here's the error propagation law, which we just discussed. It has two components. Propagation law. The first component is the previous variance, so we have p prime of the position and the current variance of the position, which is modified by the partial derivatives of the function that maps the previous position into the new position. And as I promised you, those components here are all one. It's pretty straightforward to do that. So that's the motion component. Let's write it here, motion component. And that explains the fancy growth of the y dimension over that of the x dimension. And this is simply adding the wheel slip variance, wheel slip component. And so those partial derivatives just express how the error of the wheel slip relates to the error in the positions. And so here the same thing, I have the partial derivatives. This was the right wheel component and this was the left wheel component. Here we have the x dy, so it's delta x delta y and delta theta components, and we took the derivative with respect to x. Well, it's 1, to y it's of course 0, and to theta it's 0. And here this is the y to y, it's 1. And the only thing that's really interesting is taking the derivative of the theta component with respect to x, to y, and to theta. And only here you actually see something. So the derivative of the cosine is the sine, actually negative sign. The root of the cosine of the sine is the cosine, and so on. So you can do that on your own time. I just want you to see how this looks like at the end. And now what we can do is we have all the ingredients to plug this into Matlab except one, which is the covariance matrix of the wheel slip, which is this one. And so we should define that somehow, and here I call it delta. And one way of doing this is just using the absolute value of the actual motion of the wheel and multiply it with some kind of constant k. So the more the wheel moves, the more error I get, and I can calculate this constant by doing some experiments with the robot. And of course the covariance of the position I can set to 0 in the beginning, because I know perfectly well where the robot is. Alright, so we hack that into Matlab, and first thing we do is we create some motion for the left wheel and for the right wheel, and all of this is just a vector of centimeter increments. So in this case it's 12 centimeters per step, and there are 100 steps for the left wheel and 100 steps for the right wheel, which are 10 centimeters. So we expect the robot to make a slight right turn. We now initialize the position, so the robot is at 0, 0, 0 in the beginning, and we plug in the covariance matrix for the position and initialize it to be 0 in the beginning. Now this is just some drawing stuff where we're going to draw in. And now what we're going to do is we sweep through the entire vector of steps and begin calculating the position update. And so here I created a function which you're going to look at in a second, which is using the current position x, y, and theta and taking in the current increment of the wheels as well as the current covariance matrix of where the robot is, and in return we get a new position and we get a new covariance matrix. So this is pretty much what the main forward kinematics equation says, plus the error propagation combined. Now here's some drawing stuff, and so what we're going to do is we're going to make a line from the old position to the new position, and every 10 steps we're going to show a little quiver which shows the tethered angle of the robot, so we actually get the direction. And also every 10 steps we draw an ellipse that is corresponding to the variance in x. So you see I'm taking the first element of the covariance matrix and the variance in y, which is the second entry of the diagonal. And I rotate this around, actually this is only for the drawing the ellipse itself, but now when I draw it, I actually place the ellipse at the mean, so the position x, but then I draw it, I rotate it around the current robot orientation, because the robot actually, of course, turns. So what this is, cosine, minus sine, plus sine, plus cosine, is just the standard rotation matrix around the z-axis, which you can look up elsewhere. And finally, I also draw a mesh grid of a 2D Gaussian distribution that is centered at where the robot is and has variance x in x direction and variance in y direction. And this is a little more complicated because also this Gaussian needs to be rotated, and so I actually calculate that rotation first, and I call it xr and xyr, while x and y is the true mean that is used for the Gaussian. Now let's look how that looks like, because you're probably curious to see this in action, and this is something like this. So we have the robot moving and plotting down a variance that keeps growing, and we see here that the variance in y direction grows much more so than that in x direction. And the same thing happens here, and I think I can play this again, and you should be able to actually see it. So here you see how it fills up. Let's do that again. So you see how the variance is growing, 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 and turning at the same time. Now let's look at this from the top. And you see something like this, which is probably what you expected. Alright, now let's look at the function pos_update, which contains all the meat that we have been talking about today. We have it here. And so what it does is it first implements the forward kinematics. So these are the equations that add up the wheel speeds to the change in orientation, and then finally the change in position. So this is pretty straightforward stuff. Here we set the covariance of the wheel slip, and what I do is I look at the absolute value of the motion and I divide it by 100. So let's change this value real quick. So now the variance is 10 times higher. Save this and play. And now you see that we will have much, much bigger variance than before. Alright, let's not do that. It's probably too much. Now we calculate the partial derivatives, and this is very much the same equations than on the slides. And you see here most of them are ones and zeros because nothing actually happens, and all the interesting things happen once you take the derivative with respect to theta. And we take the partial derivatives of the kinematics with respect to the wheel motion, which is this 3×2 matrix. Now I have all these metrics. I calculate the position update and finally use all my matrices in the covariance update, which is very much the equation that you've seen before. Now let's go back to this, and maybe we can have the robot drive into the other direction now for a change and see that it works. And so that's pretty much it.